Okay, so I think we will probably get started, but I wanted to really quickly explain the chess timer rules. So, despite what this chess timer here says, really the speaker has 20 minutes and the audience has 20 minutes. The chess timer is stupid and says 25, so 5 minutes is zero, just remember that. But so 20 minutes, 20 minutes. And the rule is in the first 5 minutes, the audience cannot interrupt the presenter because he needs a little bit of time to explain what he's talking about. But after that, basically it's your job to help him get to the full 40 minutes of the talk slot. So please interrupt him. I mean, if there's anything slightly unclear, it's your opportunity to jump up, and be like, nope, I don't get it. Please, can you try again? And then he can, go through it again, or if there's some interesting thing that he didn't mention, maybe he did this deliberately so that you ask. But this is supposed to be interactive, so if you're sitting there just like sleeping, you're not doing it right. You gotta kind of jump up and try to get something going, some conversation going. So at this point, I will cede to Frank.
Cool. Hi, everyone. My name is Frank, and I'm a PhD student at MIT CSAIL. So thanks for having me today at Kurion. So I'm going to present on my research a system called Sieve, and it provides cryptographically enforced access control for user data in untrusted clouds. This talk is based on a paper that was published in this year's NSDI conference. So I'm going to provide an overview of the work and a little bit of technical details. Of course, I won't be able to go through everything. And you can find more details on the paper on my website, which is frankwang.org. So to motivate Sieve, so let's consider the following scenario. So a user has a Fitbit that collects data on her fitness, like her heart rate, number of steps, miles run, etc. And this data is now stored on the Fitbit server, which acts as the user's storage provider. Now she wants to share different subsets of this data with various services. So for example, she might want to send only her running time for the New York Marathon to the New York Marathon service to participate in the leaderboard, or she might want to send her running times for other marathons to the Boston Marathon for qualification purposes, and she might want to send parts of her fitness data every month to her insurance company to receive a discount, and the list can go on. However, there's a major security issue in that model. A curious storage provider who is logged in, or an external attacker like a hacker, can leak sensitive user data from the server. Well, one naive approach is that users can always encrypt the data before storing it in the storage provider. However, in order to give the New York Marathon access to her data, she now has to give the New York Marathon her key. This is problematic because now the New York Marathon can access all her data because it has the key for all the data. So this approach allows the user to securely store her data, but the question is, how does the user selectively disclose her data? Well, the user can always... Another approach is that to encrypt each piece of data individually and distribute subsets of these keys. However, a Fitbit is constantly generating new data, and all that data needs to be encrypted with different keys. So now the user is stuck managing all these keys. So the question is, can we build a system that does this better? This leads to our research system, which is Sieve. It's a new platform that allows users to both selectively and securely disclose their data. Some of the features of Sieve is that it protects against server compromise. It hides key management from users. It has reasonable performance. We support revocation, and it's particularly useful for services that analyze large amounts of user data. So here's an outline for the rest of the talk. I'll talk about different components of Sieve, the protocol, some optimizations we make, revocation. Then I'll go on to talk about the implementation and evaluation. So here I'll present an overview of the system, not with all the kind of crypto elements involved yet, but just to kind of give you a sense of what the system looks like overall and what components are involved. So Sieve has three main principles. There's the user, the storage provider, which stores the user data, and web services, which analyze the user data. There are three main components in Sieve. There's the Sieve user client, the Sieve storage daemon, and the Sieve data import module. So to relate this back to the original example, the storage provider would just be the Fitbit cloud server, and the web services are the Boston Marathon service, New York Marathon, insurance companies, etc., etc. So first, the user using the Sieve user client tags and encrypts her data with attributes that represent access for future web services and sends this data to the storage provider. So this data can either be generated by the user directly or by a device like a wearable. And when the user first visits a web service, she generates a decryption key that corresponds to a policy on the types of data the service can access and gives this key to the web service. So later in this talk, we'll show how we can revoke the web service's access. So now the web service has the ability to download and decrypt user data. So the web service sends a user data request to download the encrypted data. And since the web service has the decryption key and the data, it can now decrypt the data using the Sieve data import module. So the web service now stores this data in its own servers and storage, and it can use it for different types of analysis. One thing to know is that all these interactions can be asynchronous. In fact, the user doesn't even have to be online after she gives the web service the key for it to access the data. Yes.
Can you go back and explain to me which keys? I'm confused about what key you're encrypting with versus.
Yeah, so I'll actually get to it later in the talk, but you usually so the system we end up using is a public key system. So you encrypt with a public key, and then you give a private key, which is a decryption key, to the web service.
Okay. I'm curious. I don't understand. I guess how the restriction happens, or there's restrictions happening on your server that.
So the restriction happens when I encrypt the data.
Prevented from decrypting all the data on the server, are they?
Sorry. Yeah, you're cryptically the key you give only allows you to decrypt a certain subset of the data.
Does the storage provider have the private key that web service decrypt?
It has a special. Each web service has a special private key that only allows it to decrypt certain parts of the data.
I'm sorry. How do you prevent the web service to share secret keys?
You can't prevent the web services from sharing the secret keys.
Repeat the question.
Oh, sorry. So the question was, how do you prevent the web service from sharing the keys? We trust the web service to hold the keys that and kind of we trust it to not give it to other web services. Or if it does, those web services can't access data that the user has given no one access to. Yes.
If you have three pieces of information, A, B, and C, and you have two web services, 1 and 2, and you want one to be able to access pieces of data A and B, and the other one to access B and C, so B is shared but not the other ones, is there any way you can do that without encrypting twice B and storing it twice with two different keys on the storage provider?
Yeah. So to summarize the question, you have three pieces of data, and there's one commonly shared piece of data between two web services. Do I have to encrypt the data twice? So we're going to use a special cryptographic scheme that makes it so you only have to encrypt the data once. And then I'll talk about that in a couple of slides. Yes.
Not the right question. So in your schema, user, does it mean the actual end user? Do you expect them to do the signing and mailing?
Yeah.
It's
So.
a kind of theoretical client.
Yeah. So the question is the user the end user, or is it a theoretical client? So we assume that if you were to use the system in practice, the user itself would use this client or download this client that allows them to share the keys and actually do it in reality. Like in practice, the users would create the key and share it. But of course, this is all abstracted away from the user. Cool? All right. So now I've given you an overview of Sieve. We'll talk specifically more about the security problems in the threat model. So we assume that the storage provider is a passive adversary, which means the adversary can read all the data on the network, but still follows the protocol. We assume that web services are trusted with user data once they're given access to it, and we trust the users and her devices. So this kind of answers some of the questions people have asking. So how do we do this? So our approach is to use this cryptographic primitive called attribute-based encryption. We assume that there's a user-specific attribute AB public and private key pair. And there are three main functions for ABE. There's the generate decryption key function, encrypt, and decrypt. So first, generate decryption key takes in a policy and an ABE private key, and it outputs an ABE decryption key. And so a policy is a predicate connected by ands and ors. For example, year is less than 2013, and type equals fitness. Yes.
Do you think of the policy as just being like a definition of a set then?
So the question was, can you just consider the policy as a definition of a set? Yes, that's one way to think about it. So to kind of add on to the question of why we think about policies and tags is because users already kind of tag their data. For example, I tag photos and stuff. And so I guess users will probably think of them as kind of just specific attributes rather than kind of a set definition. But if you're kind of a more security and privacy savvy person, you can think of it as a set. So if you have these situations where you want to commonly encrypt like one thing B, yes.
Is there a particular normal form the policy must conform to, or can you use things like negation or?
You can use negation, and it handles both integers and strings.
You have equality.
Equality and less than.
Yeah.
Cool. So the second function is encrypt, which takes in attributes, clear text, or takes in attributes, clear text data, and the AB public key, and it outputs a ciphertext. So examples of attributes are key value pairs like location equals US, year equals 2012, and type equals fitness. And finally, there's the decrypt function, which takes in a ciphertext and a AB key policy, and it only decrypts the ciphertext if the ciphertext attributes satisfy the key policy. And one important thing to note is that the attributes and policies are in clear text. So now let's look at Sieve with AB involved. As you may have noticed, AB fits very well into this architecture. So first, the user uses the AB encrypt function to tag and encrypt her data. Then she sends this data to the storage provider. When she visits a web service, she generates an AB decryption key, and she gives the AB decryption key to the web service. And now the web service can just go to the storage provider, download the encrypted data, and use its key to perform AB decryption to get the clear text data. However, there's still a few challenges with AB, specifically performance and revocation. So since AB is a public key crypto system, it's slower than symmetric key cryptography. So we want to reduce the number of AB operations that are being done. In our paper, we specifically employed two optimizations. In this talk, I'll discuss hybrid encryption. I'll refer you to the paper for storage-based data structures, which are just an extension of hybrid encryption that packs more data under one metadata block, which I'll explain later. So in hybrid encryption, first you generate the symmetric key, and that key is used to encrypt the data. And then the AB public key is used to encrypt the symmetric key and the GUID, which represents the location of the actual encrypted data block. And this way, symmetric encryption, the faster encryption method, can be applied to the larger data, and AB is applied to the small and fixed size data. And encrypting GUIDs are important for storage-based data structures, which we explain more in the paper. And both these encrypted objects are uploaded to the cloud. For the rest of the talk, the block that is encrypted with the ABE key, we'll refer to it as the metadata block. And in the storage provider, the data block is indexed by the GUIDs, and the metadata block is indexed by the ABE attributes. So for future updates, yes.
I don't know what it is.
So the question is, what's a GUID? A GUID is just an ID number. So whenever you load something, for example, to Amazon S3 or Amazon AWS, you store something there, it spits back kind of an ID. You can think of it as just a hashed ID that can get you the location of a specific object very quickly. So for future updates that require uploads by the user or downloads by the web service, the user and web services can just cache the symmetric key and GUID so it can go and just look it up directly without having to download the metadata block again. And they can use the GUID to access directly to just perform symmetric key operations only for future gets. So now I'll talk a little bit about revocation. So let's go back to our initial Fitbit example. So suppose a user now wants to switch insurance companies. So she wants to revoke the insurance company's access. However, what if the old insurance company becomes compromised in the future? Remember that the old insurance company has cached keys from hybrid encryption that it can use to access the user's data. Well, that's problematic. So we need a way to re-encrypt the data to provide cryptographically strong revocation. So how do we do that? So we need to both re-encrypt the metadata block and the data block. Well, it's easy to re-encrypt the metadata block, which is smaller than the size of the overall data. We can just download the metadata block, decrypt it, and upload it again. And since it's a small amount, it doesn't take that long. So how do we re-encrypt the data object, which might be much larger? Well, we can always just download that, re-encrypt, and upload the data object. But that requires a substantial amount of bandwidth and client-side computation. So the question is, can we do better? Yes.
The user is supposed to know when this insurance company has come evil.
So the question is, how does the user know when the insurance company has become malicious? Uh, so usually the flow of events is that I want to switch. So the point is that I want to switch insurance companies or I don't want to use it anymore. So the user has to initiate the revocation. So the user may or may not know. Maybe they don't want them to have access anymore. So the way you should think about it is now, for example, you use Facebook OAuth to grant access to a variety of things. And so, for example, you might not know something is malicious, but you might want to revoke their access anyways. Or if you know it becomes malicious, then you want to take away their access right away. Yes.
When you're saying that encrypting large pieces of data is too slow, um, how slow is it? What are we talking about? Seconds, milliseconds, years?
Um, so so I'm talking about. So the question is, how slow is this encryption method? So the encryption itself is very fast, but the problem is doing the re-encryption. So downloading the data, decrypting it, re-encrypting, and uploading again is pretty slow because you have to pay this like round trip latency cost, and that can vary based on your network latency, which could be a lot or slow. But we imagine like a user might just use her home internet, or another way of thinking about it is like it could be your mobile phone also. So it could be much slower if you're on something like 3G or 4G. Yes.
I don't understand how downloading and re-encrypting the same data with the same key is going to protect, in this case, the insurance company from decrypting that data.
So the question is, how does kind of downloading and re-encrypting help with preventing the insurance company from accessing data in the future? And so the point of kind of downloading and re-encrypting is you do it with a different key. Yeah. So yeah. Cool. So we want to be able to do this without having to pay the bandwidth cost. And so the solution is to use this cryptographic primitive called key homomorphism, which allows changing the key in encrypted data. What I mean is that it gives you a symmetric cipher that provides in-place re-encryption without decrypting the data. And the guarantees that it gives you is that you don't learn the old key, new key, or plain text. Yes.
When you say in place, does it mean that the process happens on the server?
Uh,
So you need to trust the process?
um, so the question is, by in place, do I mean that it happens on the server? It does. So we trust that the server performs the action, but the server doesn't learn any information about the data block during the re-encryption process.
Yes. Does that mean that you continuously, for all future reads from that data set, have to decrypt twice or something? Or no? Like, how does it, like, does the in-place thing work mean that they have to take the originally encrypted data, decrypt it with the original, or, no, you're remote, I'm confused.
Okay.
Keep going.
Okay. Yeah.
Once you
So the question is, when I re-encrypt, I don't need the old key at all. Yeah, I don't need the old key at all. Yeah. Maybe the next slide will clarify the whole process. But you feel free to ask a question.
So the question is, so to the organizations you trust, you give new keys, right? But not to the one that you don't trust anymore.
So the question is, does the organizations get new keys? And the answer is so it's a little bit more subtle than that. So certain organizations get new keys, and certain organizations their keys can stay the same. It depends on what data you're revoking access to. I think this next slide will help people. But if you're confused after that one, I will be happy to answer questions. So, so here I'll describe the whole revocation process. So in a simple Sieve data object, there's a metadata block with a symmetric key and an encrypted data block that's encrypted using that symmetric key, which is encrypted using ABE. So one important detail to note is that if a user wants to have revocation in their system, she has to introduce an epoch number as an attribute when she generates and tags data. So similarly, she has to include this epoch number as part of a policy for the web service keys she gives out. This number just represents the number of revocations that has happened. It could be something more clever, but just for now, let's assume that it represents the number of revocations. And the purpose of this epoch number is that during revocation, it allows users to re-encrypt just the data with attributes affected by the web service's key policy that's being revoked, rather than re-encrypt all of their data. So then the user generates what we call re-keying token, which is just a function of the old key and the new key, and sends this token to the storage provider, who applies it to the appropriate data block and then deletes the token. This causes the data block to be re-encrypted. Next, um, Next, we want to re-encrypt the metadata block. So the user just generates a new metadata block based on the new symmetric key that she used to re-encrypt the data block, and that's encrypted using an AB public key with the same attributes, but with an incremented epoch, and this now replaces the old metadata block. So the user does this process for all the data blocks that the revoked web service had access to. And finally, the user issues new keys to web services whose data access has changed and been affected by this revocation. Yes.
So what about encryption authentication? Does it deal with that, or does the client need to get involved?
So the question is, do I deal with does the system deal with authentication? So we kind of like punt authentication to kind of like the user knowing that this is the web service they actually want to access. Does that make sense? Well,
So are you talking about authentication in the sense of HMAC? Because that's what I mean.
oh yeah, so you're talking about the authentication for the data. So yeah, I didn't actually mention this in the talk. So in the data includes the data block and a signed version also in encrypted data. So there would be a piece of data and then something signed with the user's private key.
Okay, but in that case, okay. So does the re-encryption scheme re-sign that, or does the client then need to get involved in re-signing the new data?
Yeah, so the data right there, like that says data, that includes actually the actual data block and a signed version encrypted. Like they're all so the signatures don't get affected during re-encryption because the signature itself is also encrypted.
Oh, okay, so it's not say encrypt then MAC. It's kind of all in there.
Yeah, so it's encrypted. It's encrypt. It's sorry.
Oh, it's encrypt and sign.
It's signed and encrypt.
Or sign and encrypt.
Yeah, which is fine because it's different from a Mac. Cool. Now I'll talk a little bit more about the implementation and evaluation. So for the Sieve implementation, we use for cryptography this ABE library called libfanc, which uses the Stanford pairing-based cryptography library, and we implement it with two different symmetric ciphers: AES, which has no revocation, and randomized counter mode with ED448, which has revocation. And so the Sieve user client has about 1,400 lines of code. The Sieve storage daemon has about 1,000 lines of code, and we use MongoDB and BerkeleyDB in the background. And the Sieve data import module really depends on the web service you use, which leads to our evaluation, which looks at two major questions. Is it easy to integrate Sieve into existing web services, and can web services achieve reasonable performance while using Sieve? And for the evaluation setup, we use a multi-core machine with 2.4 gigahertz Intel Xeon processors, and the web services we ran on machine loopback. So numbers you see will have almost no network latency, so we can see what the cryptographic overheads are. And we have two major case studies that we integrated with. One is this piece of software called OpenMHealth, which represents small data and helps you visualize health data. And a week's worth of health data is about 6 kilobytes. And we have another photo service called Piwigo, which has much larger data, and the service allows you to edit and display photos. And one photo is about 375 kilobytes. And so we show that it's pretty easy to integrate with Sieve. So the lines of code required for integration, it's about 200 lines for OpenMHealth, about 250 lines for Piwigo. And so here are just some results for OpenMHealth and Piwigo using ED448 with key caching. We have acceptable performance for both case studies. We see that reading and writing a week's worth of OpenMHealth data takes less than a second, and the read and write time for Piwigo is longer because the data is larger. And so there's a performance gap between AES and ED448. Yes.
You said one photo is 300 something, but how many photos do you have in this benchmark? One photo or?
So the question is, how many photos are there in this benchmark? There's only one photo. Cool. So here we just show there's a performance gap. However, this is because ED448 is less optimized than AES, which has hardware support. But we expect this performance to improve in the future with more research and better hardware support. And I'll mention near the end of the talk some more engineering optimizations that we can make, and we looked into after we published this paper to improve the numbers a little bit. And so the server per core throughput is pretty good. We can get about 50 megabytes per second for OpenMHealth, and we can import about 70 users worth of data per minute. For Piwigo, yes.
ED448 is the symmetric algorithm that you're using?
Yes.
Why would someone choose to use ED448 if both AES exists and is good and is fast?
So the question is, why would you want to use ED448 instead of AES? So AES doesn't allow us to do revocation, whereas ED448 does. So yeah, the reason is because ED448 is key homomorphic, and so as a result, with more structure, it's going to be a little bit slower.
And would AES ever become key homomorphic?
So the question is, can AES ever become key homomorphic? The answer is not in its current state. It won't be AES. It has to be something different. You can't use AES
so
because
the way forward would be to go to have hardware support for a symmetric cryptographic algorithm that is key homomorphic.
Yes. All right. Cool. Awesome. So the revocation performance is also reasonable. We can re-encrypt a metadata block in 0.63 seconds. We can rekey a 100 kilobyte data block in 0.66 seconds. And we can generate a new 10 attribute key in 0.46 seconds. So I wanted to kind of make some last remarks about Sieve and the performance. So first, this is not restricted to just Fitbit cloud data. The question is, who are these storage providers? The storage providers can be Amazon EC2, Google Cloud, Facebook, Twitter, really any system that has large amounts of user data that can be shared. And second, I showed you some performance numbers, but those are for a research prototype to just show its practicality. And the performance can be substantially improved in, I think, two main ways. First, we can build faster ABE libraries that use assembly-based pairing libraries. So my initial benchmarks for this new library called DCLXVI, so that has a lot of potential. It takes about 0.5 milliseconds to do a pairing, but I'm not sure how this will translate into the ABE world. And next, we can build faster large integer libraries that will make revocation much faster. Currently, we use libgmp, but it's not really clear to me what the limiting factors for faster large integer libraries is, and it's definitely worth looking into. And these are just kind of a couple of ways to optimize and improve the performance of the system. And it's important that we work with industry to focus on engineering efforts to reduce cryptography bottlenecks. And here are just some yes.
Just some bad news for you. The Gene key is pretty well researched, and don't expect anything more than maybe 10 or 20% speed up if you really, really try hard.
Okay. No. All right. Cool. Yeah, just to conclude, I present a new access control system that allows users to selectively and securely expose their private cloud data to web services. It efficiently uses AB to manage keys and policies. There's a complete revocation scheme that's compatible with hybrid encryption using key homomorphism, and it's easy to integrate and has reasonable performance. And I just wanted to thank a few of my collaborators, James from Harvard, Nikolai and Vinod from MIT, who helped me bring me one paper closer to graduation. And there's more information about this paper on my website, frankwang.org, and you can follow me on Twitter.
So you got another minute and 45 seconds of speaker time and about 8 minutes and 20 seconds of audience time. So
Okay.
actually, oops.
I have two questions about policies, if I may. So first one, how schema sharing is supposed to happen? So how does a web server supposed to know about which tags and which policies are available for my user data?
So the first question is about, this is your first question is about how does the web service know about the schema?
Yeah,
Um,
tags.
Yeah, so that was one issue we kind of ran into. And the answer to that is we kind of assume that everyone ends up using maybe a standardized schema, or the web service tells the user, yeah, you should store your data in such a way, or there's some standardized schema that everyone uses. You can imagine people using some form of XML or JSON, or kind of like working through different types of schema. But yeah, it's something we haven't really looked into, is the short answer.
And the second one, I just didn't quite get it from your description of revocation. If I share the same tags, the same policy, same tag with two providers, and I revoked the key for one of them, will the second one still have the access to, or due to the encryption, it will override their access?
So the question is if there are two services that have the same policy, or the
Same
same.
tag, let's say,
They,
fitness data. I shared fitness data with two providers, right?
oh, okay. So the question is, if two providers should access the same data, if I revoke one access, will the other one still have access? And the answer is yes. So the way we do it is after you revoke, you have to send new keys, a new key to the one that had access to that you want to access the fitness data. So the non-revoked one, you would set in a new key, which is just the same key, but then there's an epic number, and you just increment it by one. Yes.
Does that imply that anytime I generate a key with the same policy, uh, the the generated key is the same for everyone I give it to? It's not individual. The epic number is what separates them.
So the question is if the policy is the same, is the key the same? If the answer is yes. If the policy is exactly the same, not include like everything, including the epic number, then you get the same key. But if there's any small variations, a different key. So that's why the epic number gives you a different key. Yeah.
So you're talking been focusing on talking about how to control which service providers can decrypt a data block. Does this scheme also prevent service providers from knowing about the existence of data blocks that they should not be able to access?
So the question is, I talk about mostly access control for giving selective access. The question is, do web services know about data blocks they cannot access? So hypothetically, they shouldn't unless the storage provider tells them. So the storage provider has kind of a mapping from kind of the different tags to the data. So it maps attributes to the data. And so, for example, one way the service provider could learn whether it has access to certain data or not is to just like ask for data it's not allowed to access and then try to see if it decrypts it. And I mean, the storage provider could offer some form of kind of like filtering in that case. But yeah, it is possible for them to discover what blocks they can't access, but they can't actually access the actual data, even though they discover like I don't have access for fitness data, for example, but they can't decrypt the data for that. Yes.
So how confident would you be about using this in production?
So the question is how confident I am about using this in production. Not my research prototype, but I'm pretty confident on at least pieces of the system actually working. So I've been talking to kind of a variety of people. There's some interest with certain groups actually at Google and at like ETH Zurich, which are actually interested in kind of like using this into like different production systems or like into their other research projects.
So is there anything that, say, weakens the or is there anything that makes this potentially weaker than the standard encryption? Is there anything that sort of, if I just use AES, forget about humans and revocation and all that, is there any step at which you think, well, this is maybe not provably secure, therefore it might compromise the whole system, or is that not the case? If that makes sense.
Um, can you repeat the question?
So you're using some methods, like if you told me, oh, I'm only using AES, then I'd say, okay, AES is fairly well proven and blah, blah, blah. Like, you're using presumably some binary maps and other stuff to achieve this. Is this all provably secure? Is the stuff you're building on top provably secure, or are you confident via some non-scientific means that it's pretty good and it's not going to get compromised? Or is it completely unknown?
Okay. Oh yeah. So the question is the cryptum schemes I'm using or the methods I'm using, are they provably secure or kind of or if I feel confident about it. They are provably secure. So ABE is a provably secure scheme. It's been pretty well studied. It came out in 2006, and people have kind of studied it for the last 10 years in various different settings. And it's all provably secure. Same with kind of this key homomorphic encryption that we're also using.
What about the public key crypto system? What provably secure public key crypto system are you relying on?
So the question is, what provably secure public key crypto system am I relying on? So ABE is actually a provably secure public key system that we're using in this scheme. Yes. Yes.
I understand that this is, of course, not used in production yet, but are there plans to integrate it into anything? I don't know, something?
So the,
AWS, for example, Google Cloud Storage. Can I use it anytime soon?
Um, so the so the question is, so this isn't used in production right now. Can I use it anytime soon? And the answer is maybe. And I think the point is, I think parts of it are very interesting to different people. I think it's just a matter of finding the right applications for people to use it. I think a lot of interest is actually around using the re-encryption system, which is pretty convenient because a lot of times like data sits on the cloud and it's encrypted, and people don't want to decrypt it on the cloud and re-encrypt it in the cloud. So if you use something like Amazon right now, they actually have key rotations, and what they do is that they generate a new key, decrypt the data, re-encrypt it, kind of like all in the cloud. So if you have kind of a malicious person just hanging out in the cloud, they can kind of they wait for you to decrypt the data or the key rotation to happen. I think there's a lot of interest from that end. I think like people are interested. For example, there's this new system called Keybase, and they're very excited about like doing re-encryption and revocation. It's just the speeds aren't fast enough, and so if we can kind of like think of better key or faster key homomorphic schemes, like I think that would help a lot for getting us closer to production. Yes.
Can you use this in a setting where the web services are also simply clients and I'm trying to share my baby photos with different members of my family, for example? Like each one has an app on his phone. So can you replace web services with clients but still use the same infrastructure?
So the question is, can you replace web services with clients and use the same infrastructure? And the answer is yes. So web service can be anyone. It could just be another user if you want it to be. Um, yeah, there's no restriction on that.
I mean, there's only like a minute left, but if everybody is satisfied, we could draw this to a close then. So thank you very much, Frank, for
Yeah, thanks.
for grading the first chess timer talk.
Distribute subsets of these keys. However, a Fitbit is constantly generating new data, and all that data needs to be encrypted with different keys. So now the user is stuck managing all these keys. So the question is, can we build a system that does this better? This leads to our research system, which is Sieve. It's a new platform that allows users to both selectively and securely disclose their data. Some of the features of Sieve is that it protects against server compromise. It hides key management from users. It has reasonable performance. We support revocation, and it's particularly useful for services that analyze large amounts of user data. So here's an outline for the rest of the talk. I'll talk about different components of Sieve, the protocol, some optimizations we make, revocation. Then I'll go on to talk about the implementation and evaluation. So here I'll present an overview of the system, not with all the kind of crypto elements involved yet, but just to kind of give you a sense of what the system looks like overall and what components are. Time for the New York Marathon to the New York Marathon service to participate in the leaderboard, or she might want to send her running times for other marathons to the Boston Marathon for qualification purposes, and she might want to send parts of her fitness data every month to her insurance company to receive a discount, and the list can go on. However, there's a major security issue in that model. A curious storage provider who is logged in, or an external attacker like a hacker, can leak sensitive user data from the server. Well, one naive approach is that users can always encrypt the data before storing it in the storage provider. However, in order to give the New York Marathon access to her data, she now has to give the New York Marathon her key. This is problematic because now the New York Marathon can access all her data because it has the key for all the data. So this approach allows the user to securely store her data, but the question is, how does the user selectively disclose her data? Well, the user can always... Another approach is that to encrypt each piece of data individually and...
Just like sleeping, you're not doing it right. You gotta kind of jump up and try to get something going, some conversation going. So at this point, I will cede to Frank.
Cool. Hi, everyone. My name is Frank, and I'm a PhD student at MIT CSAIL. So thanks for having me today at Curion. So I'm going to present on my research a system called Sieve, and it provides cryptographically enforced access control for user data in untrusted clouds. This talk is based on a paper that was published in this year's NSDI conference. So I'm going to provide an overview of the work and a little bit of technical details. Of course, I won't be able to go through everything. And you can find more details on the paper on my website, which is frankwang.org. So to motivate Sieve, so let's consider the following scenario. So a user has a Fitbit that collects data on her fitness, like her heart rate, number of steps, miles run, etc. And this data is now stored on the Fitbit server, which acts as the user's storage provider. Now she wants to share different subsets of this data with various services. So for example, she might want to send only her running involved. So Sieve has three main principles. There's the user, the storage provider, which stores the user data, and web services, which analyze the user data. There are three main components in Sieve. There's the Sieve user client, the Sieve storage daemon, and the Sieve data import module. So to relate this back to the original example, the storage provider would just be the Fitbit cloud server, and the web services are the Boston Marathon service, New York Marathon, insurance companies, etc., etc. So first, the user using the Sieve user client tags and encrypts her data with attributes that represent access for future web services and sends this data to the storage provider. So this data can either be generated by the user directly or by a device like a wearable. And when the user first visits a web service, she generates a decryption key that corresponds to a policy on the types of data the service can access and gives this key to the web service. So later in this talk, we'll show how we can revoke the web service's access. So now the web service has
Okay, so I think we will probably get started, but I wanted to really quickly explain the chess timer rules. So, despite what this chess timer here says, really the speaker has 20 minutes and the audience has 20 minutes. The chess timer is stupid and says 25, so 5 minutes is zero, just remember that. But so 20 minutes, 20 minutes. And the rule is in the first 5 minutes, the audience cannot interrupt the presenter because he needs a little bit of time to explain what he's talking about. But that after that, basically, it's your job to help him get to the full 40 minutes of the talk slot. So please interrupt him. I mean, if there's anything slightly unclear, it's your opportunity to jump up, and be like, nope, I don't get it. Please, can you try again? And then he can, go through it again. Or, if there's some interesting thing that he didn't mention, maybe he did this deliberately so that you ask. But this is supposed to be interactive, so if you're sitting there